Hello, we are group B22 for EECS 203 and we're doing our presentation on the Fibonacci sequence. I am Colin Yokish and my group members are Jim Rashi, Whitney Wang, and Ronak Mehta. What the Fibonacci sequence is a sequence of numbers 0, 1, 1, 2, 3, 5, 8, and so on. What it is every number is the sum of the two previous numbers. So we have f of 0 equals 0, f of 1 equals 1, and then f of anything greater than 1, f of n, equals an minus 1 plus an minus 2, where a equals f of n minus 1 and n minus 2. So for any sequence of numbers, you can solve for the next number. So if let's say we wanted to find the Fibonacci sequence of f of 7, the eighth term of the Fibonacci sequence. So what you do is you have f of 0 equals 0, or equals 1, f of 0 equals 0, f of 1 equals 1, f of 2 equals 1, and you can just keep going. F of 3 equals 2, f of 4 equals 3, f of 5 equals 8, or equals 5, f of 6 equals 8, and then f of 7 would equal 13. As you can see, this can get pretty tedious for higher level Fibonacci sequences, and a computer can be used to calculate those out to a larger value. But for any Fibonacci sequence, you can calculate it with this sequence f of 0 equals 0, f of 1 equals 1, and then f of n equals f of n minus 1 plus f of n minus 2. And that will take care of any Fibonacci sequence you can think of.
In the year 1202, Fibonacci became interested in the reproduction of rabbits. He created an imaginary set of initial conditions under which the rabbits could breed. First off, he said that you would start with one male and one female rabbit. And it takes 1 year for these rabbits to reach reproductive maturity. Once at reproductive maturity, the females would give birth once a month. And the litter that they birth would have only one male and one female rabbit each. For the sake of this experiment, rabbits would never die. The question Fibonacci wanted to answer was, after a given amount of time, how many rabbits would there be? And with this thought experiment, he found a pattern in the number of rabbits. So the first month, you would just start out with the pair of rabbits. In the second month, they would become pregnant, but it takes 1 month to create a child in the rabbit universe, so they would not produce it now. So in the first and second month, you only have still one pair. In the third month, the pair would give birth to another boy, another girl rabbit. So there would be 2. Now these rabbits are pretty terrible, but that's about as good as it gets. In the fourth month, the newborn rabbits would not yet be reproductively ready, but the first original pair would also produce another set of bunnies, as they would get pregnant right after delivering the first generation. So that creates 3 pairs of rabbits. This pattern looks familiar. It definitely is, and this is the foundation upon which Fibonacci came up with his infamous series that bears his name.
Another interesting application of Fibonacci sequence is that it's directly related to the Pascal triangle. The Pascal triangle looks like this. The next number is the sum of the numbers 2 before it. It's the shallow diagonals that form the Fibonacci sequence. 1, there's 2, there's 3, there's 5, and there's 8. And if you continue, you'll see that you get the rest of this Fibonacci sequence, 13, 21, 35, and so on. Another interesting application of the Fibonacci sequence is with right triangles. Starting with 5, every second Fibonacci number is the length of the hypotenuse of a right triangle with integer sides, or in other words, the largest number in a Pythagorean triple. The length of the longer leg of this triangle is equal to the sum of the 3 sides of the preceding triangle in this series of triangles, and the shorter leg is equal to the difference between the preceding bypassed Fibonacci number and the shorter leg of the preceding. Now that was a lot of words. Let's see if we can show this with some pictures. We start with the basic Pythagorean triple that we all know, the 3, 4, 5 triangle. Now to get the next one, we look at the next second number in the Fibonacci sequence, 13. That becomes our hypotenuse. The longer side of this triangle becomes the sum of the previous triangle's sides. 3 plus 4 plus 5 equals 12. And now the shorter side of this triangle is the number we skipped over, 8, minus the shortest side of the triangle that we just did, 3. 8 minus 3 is 5. And so on, we can see that the next triangle will be 13, skip 21, 34. The longer side will be 5 plus 12 plus 13 equals 30. And the shorter side will be the number we skipped, 21, minus the shorter side, 5, is 16. Another interesting result of the Fibonacci sequence is a sort of golden spiral that exists in nature. If we take a regular rectangle of dimensions of 2 repeating numbers of the Fibonacci sequence, let's say 8 and 13, then we can see by splitting consecutive rectangles in half, we can form an interesting spiral. So from 13, we split at 6.5, and at 8, we split at 4. And now at 6.5, we split at 6.25, and at 4 we split at 2, and so on. Now from this, if we start in this corner and draw spirals into the opposing corner of each rectangle, we get this golden spiral, like this. And so on. Now this golden spiral appears in many places in the universe and in our own backyards. The nautilus shell, commonly found on beaches, has shells in the form of a golden spiral, and many galaxies that have spiral shapes are of the form of the golden ratio. Now this golden ratio has a unique connection with the Fibonacci sequence. It is the limit as we get further and further into the Fibonacci sequence of the number that we're looking at over the previous number. Now this looks confusing, but it's actually just, let's say we start with the first couple numbers, 1, 1, 2, 3, 5, 8. Take 1 over 1, that's 1. 2 over 1, that's 2. 3 over 2, that's 1.5. 5 over 3, that's 1.6. 8 over 5, that's some number, and so on. We can see that this seems to be approaching some number around 1.6. This number is normally approximated to be 1.618.
Research has been conducted linking physical beauty and symmetry. For example, the standard of beauty, measured by opinion testing, has revealed that a face with a length of about 1.6 times its width is the most appealing facial type. Also, another occurrence in human beings is that the length of the average human forearm is usually 1.6 times the length of the hand from your middle finger, the end of your middle finger, to your wrist.
As we've stated before, the golden ratio number is approximately 1.618. This can be found in many real-life applications, such as in geometric constructions, as shown here. The ratio of the whole line A to the large segment B is the same as the ratio to the large segment B to the small segment C. In other words, A is to B as B is to C. And this only occurs where A is 1.618 times B and B is 1.618 times C, which lends itself more to the golden number. Across the world, this can be seen in many different things. In Egypt, you can see it in the Great Pyramids. In Greece, you can see it in the design of the architecture, and even in painting and art, you can see it into the proportions laid out in the Last Supper. Also, you can see it in Paris and Notre Dame, and it continues in many other examples of art, architecture, and design.